All right, here we go. Unit 1, motion and forces. It's been a little while since I made one of these videos, so let's see how it goes. All right, so I'm going to write up the solutions and just kind of talk through it as I do it. Okay, consider the position versus time graph below for two cyclists, A and B. All right, A, so A is going a nice constant velocity up. It's going the same distance each time. B appears to be starting ahead of A and moving at a slower constant velocity forward. So do the cyclists start at the same point? No. A starts ahead. Its position at time 0, meaning 0.0 seconds. Oops, sorry. B starts ahead. Its position at time 0 seconds is greater than A's, right? So if I was going to draw a picture of this, so this is B's initial position right there. X initial, I'll call it. This is A's X initial B. This is A's initial position. So A's initial position is 0. B's initial position is something positive. If I was going to draw a picture of this, right? Here's cyclist A. All right, starting at 0 meters, and cyclist B, this is A, cyclist B is starting out in front of A, some position greater than 0. Okay, so t equals 7 seconds, which cyclist is ahead? So 7 seconds, maybe let's just say that's 7 seconds. It's somewhere to the right here, right? A is ahead because A has a greater position value. Greater position value. These little at 7 seconds. All right, yeah, this is the position. There's B right there, A's farther ahead. Which cyclist is traveling faster at t equals 3? How do you know? Well, 3 seconds is probably, I don't know, like right here. Well, I know because the slope, the magnitude of the slope of the x versus t line is the speed, all right, my writing here, of the bicyclist. Cyclist. So A has a greater slope. Use your slopometer, right? Hold it tangent to the curve. At 3 seconds, A has a greater slope than B. A has a greater slope. So A is always moving faster. Are their velocities equal? No. The slopes are never the same. Slopes are never the same. Remember, it's the slope of the line, right? A slope is constant, fairly big. B slope is constant, fairly low. So A always has a bigger velocity than B. What's happening at the intersections of lines A and B? Okay, so that's this part, this intersection. That's when A, right, has caught up to B. B's just, I'll use little arrows to represent B moving, right? B's just moving nice and slow. Well, A, I'll put some arrows up here to represent A moving. A is moving fast. So A's moving fast. So at some point, A is going to catch up to B and pass it. So A is passing B. They are at the same position at the same time. Same position, same time. A is passing B. All right, very good. Let's go on to the next page. Consider the new position versus time graph. So this is the new one for cyclists A and B. How does the motion of cyclist A in the new graph compare to that A in the previous? Well, the initial position of them, A started down here, right? This was the initial position of A in the previous graph. This is it now. Well, look, that's where A ended last time, right? So A is starting way in front or ahead of B. And not only are they starting ahead, A now has a negative slope. So that means A actually now, so if I was to draw this, this is 0. I'm just going to represent B with a, there's B. A is starting and B is moving that way slowly. A is starting way over here and moving that way quickly. So A is moving towards the starting line. From the end of the track, maybe. All right, moving towards the starting line from the end of the previous graph, basically. How does the motion of cyclist B compare? Well, they're the same. All right, same y-intercept, which means same initial position, same slope, which means same, identical. It's exactly the same. Which cyclist has a greater speed? How do you know? A still is greater. Because the slope of the line is steeper. All right, the slope of the line is steeper, which also means that it's covering more distance per time. Remember, slope is rise over run, so if the slope's steeper, that means it's covering more distance in the same amount of time. Describe what is happening at the intersections of lines A and B. Well, when they intersect, it's just when they're passing each other. They're passing each other, I guess I would say. A and B are passing each other. All right. Which cyclist has traveled a greater distance during the first 5 seconds? All right, let's go back to the graph. 5 seconds, that's where they cross paths, right? Which one has covered a greater distance? Well, B has gone from here to here. That's the distance, that's the D of B. That's how far B has gone. A has gone from finish all the way down to there. So, in fact, the distance of A is greater. Greater. Changes position more. All right, greater change in position, therefore more distance. Very good. Distance of A is greater. Changes position more. It's traveling faster over the same amount of time. A number of ways you could say that. All right, what's the difference between speed and velocity? Well, speed is simply how fast something is moving. All right, velocity is how fast and in what direction something is moving. How fast and what direction. So this could be okay, the car's going 10 miles per hour. The car's going 10 miles per hour to the east. So just 10 miles per hour by itself is the speed. 10 miles per hour east is the velocity. All right, we got a few word problems here. Tom, a physics student, walks a distance of 5 meters in 3 seconds. Determines Tom's average speed. All right, that's distance, D. That's T. Average speed is V. All right. Determine Tom's average speed. So show all of your work, including substitution with units. Well, that means write the equation. D equals V over T. Or, geez. Oh, it's going to be ugly. V equals D over T. My bad. All right, so V equals 5.0 meters in 3.0 seconds. Now, we can do this math in our head, but that's okay. 5 divided by 3. Uh-oh, what's going on here? This calculator is... Oh, no. It's like... I can just hold down and clear. Oh, well. There we go. 5 over 3, 1.67. It is about 1.7 meters per second is the average speed there. So it's a nice simple one to get started. All right, you identify the variables. There's the equation. Speed or velocity was distance or displacement over time. Number 5, a CBA physics student goes on a college visit to RIT in Henrietta, which is about 88 miles. That's our D, the distance. How fast will the CBA student have to drive? So it looks like we're looking for V in order to make it RIT in 1.5 hours. That's our T. All right, so velocity or speed equals distance over time. Looks like V is going to be equal to 88 miles per 1.5 hours. So 88 divided by 1.5 gives us about 59 miles per hour. 59, and notice, you don't need to get fancy here. It's miles on top, so I'm going to write miles. Hours on the bottom, I'm going to put hours on the bottom. 88 divided by 1.5, that gives us that. 59 miles per hour on average. So that's taking into account stop signs and everything. So your average speed for the whole trip has to be that. Race car travels at a top speed of 80 meters per second. There's V. Determine how long it will take. So determine how long it will take. All right, that's T. To make a lap around a 2 kilometer track. That's the distance. Show all your work, including the equation of substitution units. So V equals D over T. So we're looking for T here. T is our big unknown variable. All right, back here in these problems, I probably should have listed D equals 5.0 meters, T equals 3.0 seconds, V is the unknown, right? D is 88 miles, T equals 1.5 hours, and V is the great unknown. Over here, D equals 2 kilometers, V equals 80 meters per second, and T is the great unknown. All right, so check it out. 80 meters per second, 2 kilometers. Any length units in your work, they need to be the same. I I think it's going to be easiest just to make this into meters. So 2 kilometers is 2,000 meters. All right, so now let's look at our formula. V equals d over t, so it's 80 meters per second equals 2,000 meters divided by t. So we need to solve this formula for t. Well, to do that, you multiply both sides by t. All right, whatever you do to one side of the formula, you have to do the other. Cross that out. All right, but now I need to isolate the t on this side. So I divide both sides by 80. And meters per second. Let me write the units down to show you how to do this. So divide the numbers, then we'll divide the units. So 2,000 divided by 80 is 25. So t equals 25. And the units are 2,000 meters per 80 meters per second. Meters per second. The meters cancel, and you're left with 25 seconds. All right, so there's that. First few pages of the packet. All right, I'll write up this other part. I'll put it in with this video. We'll be getting to this soon enough. All right, so this is a little bit different. These are velocity versus time graphs. All right. Actually, you know what? I'm going to just introduce these and then kind of package it all together for next time. Velocity versus time graphs. Position versus time graphs. They're different. On this graph, you need to plot what the velocity was while it was moving over these time intervals. So let's just go by second. So what's this object's velocity for the first second? Up 1 over 1. Up 1 meter in 1 second. All right, so it made 1 meter per second for that first second. So that means this is positive 1. Now, we have negatives here, notice. That's if the slope of the position versus time graph is negative. We'll use that. All right, from 1 to 2, it's up 1 meter over 1 second. In fact, it's simply 1 meter per second the whole time it's moving, right? So this is the velocity versus time graph is just 1 meter per second the whole time. So the slope of this equals velocity. Slope of position versus time equals velocity. It's positive 1 meter per second. So it's positive 1 the whole time. All right, this one, and I only went to 4 because this only goes to 4. This one has a couple different slopes. Let's go ahead and figure that out. So in the first second, it's plus 2 over 1 meter per second. So that's 2 meters per second for the first second. And then the slope immediately changes to up 1 meter over 2 seconds. So the slope changes of position versus time to half of a meter every second, which means this has to go down to half of a meter per second for the rest of the motion. All right. So the final one here, we have a positive slope up 2 over 2. Up 2 over 2, up 1 over 1, up 1 over 1. So the first 2 seconds, it's plus 1 meter per second. This was plus 0.5 meters per second. Okay, so that's plus 1 meter per second for 2 seconds. And then it flops to a negative slope. That means a negative velocity. So it goes down 2 over 1, down 2 over 1. So it drops to negative 2 meters per second. And again, I only extend this one to the 4 as well. So negative 2 meters per second is the slope on that part. That's where I'm going to stop. I'll get this posted. See ya.